Types of proof. Most of the time we've dealt with deductive proof. Geometry, I guess, being the most common place that we do it. But deductive proof is, of course, when we use known facts to go and deduce what we are trying to prove. So in geometry, our known facts are our different theorems and what have you. Inductive proof is, of course, we saw in extension 1. And that's where we assume what it is we're trying to prove and try to induce the solution. There is a third sort of proof that we did look at, you might remember, proof by contradiction. We don't use it that often, but that's where we assume the opposite of what we're trying to prove. And then hopefully somewhere in our proof we come up with a contradiction and say, well, hang on a sec, these can't both be true, therefore my original assumption must be wrong, and we can then assume the counter-argument. Right, some techniques for solving these inequality type questions that we get in extension 2. When you want to prove x is greater than or equal to y, sometimes it's easier to prove x minus y is greater than 0. Let's go back to an old question, very old one, but it is one of the key questions, proving that pq is less than or equal to p squared plus q squared on 2. So I'm going to use that idea of I'm going to move everything to the left-hand side. I'm going to try and show that everything here is positive. If I create a single fraction, then on the top you'll see we have a perfect square. And perfect squares, of course, are always greater than or equal to 0. So yes. And now that I know that's a fact, I can rearrange it and go, oh yes, well that means p squared plus q squared on 2 is greater than or equal to pq. Remember, you can't manipulate what it is you're trying to prove. You can manipulate facts, you can change what it is that you want to prove to something else, but you can't sort of multiply both sides by a number of things like that. You don't know it to be true. Okay. Could have done this one by contradiction, just to show you a proof by contradiction. Not suggesting that you would, but you could. Let's assume that, actually, no. PQ is greater than p squared plus q squared on 2. Now I've assumed that to be a fact. So because I'm assuming it to be a fact, I can manipulate it. So 2pq is greater than p squared plus q squared, which means 0 ends up being greater than p minus q squared. But hang on a sec. We know p minus q squared has to be greater than 0. Well, it can't be both. There's the contradiction. So it must have been my initial statement, my assumption is false. So therefore PQ is actually less than or equal to. 1994 had a few parts to it. We're going to prove a squared plus b squared plus c squared greater than ab plus bc plus ac. Another idea we often use is starting with a known fact. So that's the deductive idea. So I'm going to start with the fact that I know a minus b squared is greater than 0. Right, we're assuming a is not equal to b here. Therefore, a squared minus 2ab plus b squared is greater than 0. So I know a squared plus b squared is greater than 2ab. But a and b are just random pronumerals. I could have used any pronumeral. So therefore, it's true also to say a squared plus c squared is greater than 2ac. B squared plus c squared is greater than 2bc. Treat it as simultaneous. Now divide everything by 2, and we get the result that we're looking for. A squared plus b squared plus c squared. So that's another common idea of starting with a known fact and working from there. This time for part B, they've told me that a plus b plus c adds up to be 1. We're going to prove ab plus ac plus bc is less than a third. Well, a squared plus b squared plus c squared, using that common idea, we often use it in probability, we often use it in sum and product of roots, same sort of idea, but it's that expression again. A plus b plus c all squared minus 2 times ab, ac, bc. So I can play with that. I can say, well, hang on, that means that a plus b plus c all squared minus 2 lots of ab plus ac plus bc is greater than. Why? Well, because back in part A, we said a squared plus b squared plus c squared was greater than ab plus ac plus bc. Okay. Well, if I move the 2ab, remember, this is a known fact because I've used what it is I proved up here, so I'm allowed to move things from side to side. I get 3ab plus ac plus bc is less than a plus b plus c all squared. But we've got the condition a plus b plus c is equal to 1. So I can sub the 1 in, divide by 3, I've got my result. Prove a third of a plus b plus c greater than or equal to the cubed root of abc. Okay, remember we proved back in part A, so going back to that again, that a squared plus b squared plus c squared is greater than or equal to ab plus ac plus bc. If I move everything to the left, I know that to be greater than or equal to 0. I'm now going to multiply everything by a plus b plus c. So both sides. Now, a, b and c are positive numbers in this. So it doesn't change the inequality sign. It doesn't necessarily equal 1. It was only equal to 1 for the part B of the question to do that one. So it might not necessarily be 1, but it's going to be a positive number. Well, if I expand that whole thing out, if you look closely, there's a lot of things cancelling there. What we've actually got is that. You've got an ab squared here. Somewhere there should be a, there it is, minus ab squared. And so on. So there's all these terms are cancelling. And I'm just left with a cubed plus b cubed plus c cubed minus 3abc. So a third of a cubed plus b cubed, oh, that's close to what I want. But remember, a, b and c could be anything. Could be x, y, z. Could be p, q, r. Could be a to the power of a third, b to the power of a third, c to the power of a third. So let's change a, b and c into a to the power of a third, b to the power of a third, c to the power of a third. Well, a to the power of a third cubed is a, and b to the power of a third cubed is b, and c to the power of a third cubed is c, and then on the right hand side I get a to the power of a third times b to the power of a third times c to the power of a third, which is abc to the power of a third, which is the cube root of ABC. Hence I've got my result. Right. Look, that last one brings up a really common idea that we use in inequalities. And that is that the arithmetic mean is always greater than or equal to the geometric mean. Now, arithmetic mean is what you understand to be average. What it is actually to do with is series and sequences. Because you have arithmetic series and you have geometric series. If you've got two terms and you want to place a number in the middle and make it arithmetic, then we would find the average of the two numbers, or the arithmetic mean. If you wanted to turn it into a geometric series, then you would find the geometric mean. Now the geometric mean, instead of adding all the numbers together, you multiply all the numbers together. And instead of dividing, you find the nth root. Always turns out that the arithmetic one will be greater than or equal to the geometric one. You can quote that, unless of course, like that last question, that's what it is you're trying to prove. I mean, I couldn't have done that last question by just going, oh, arithmetic mean is greater than geometric mean, thanks very much. No, it wouldn't work that way. Okay, so let's go to part D of this question now. Suppose that 1 plus x, 1 plus y, 1 plus z is 8. We're going to prove x, y, z is less than or equal to 1. I'm going to do it two ways. The first way you're going to love. Watch this. Now if I was to expand out 1 plus x, 1 plus y, 1 plus z, you get this beautiful expression here. Now I know a third of x plus y plus z is greater than or equal to the cube root. So arithmetic mean, geometric mean. So x plus y plus z will be greater than or equal to 3 times the cube root of x, y, z. But you know, x, y and z, they were just pronumerals. I could have put anything there. So instead of x I'm going to have xy, instead of y I'm going to have yz, instead of z I'm going to have xz, which means on the right hand side I'll have the cube root of xy times yz times xz. Okay? They're just pronumerals. I can replace x with xy, that's fine. So we get 3 times the cube root of x squared, y squared, z squared. Okay. So I've got x plus y plus z, x, y, z, what else we got there? Remember, we were told that's equal to 8, weren't we? Okay. So therefore, that must be less than or equal to 8. Because this is less than x plus y plus z, and this second bit is less than So that's less than or equal to 8. 1, 3, 3, 1. You see that x, y, z? I could rewrite x, y, z as the cube root of x, y, z cubed. 1, 3, 3, 1. The powers go 0, 1, 2, 3. Oh, hang on. That's just 1 plus the cube root of x, y, z cubed. Now, I'll take the cube root of both sides. Then now I've got the cube root of x, y, z is less than or equal to 1, which means x, y, z is less than or equal to 1. There's our proof. Well, I didn't say that was the easy way of doing it. I said it was the nice way of doing it. Isn't that a beautiful way of doing it? Okay, there's another way. It's not as much fun, but you'll all probably want to do it this way. I could have said 1 plus x is greater than or equal to 2 times the square root of x. Arithmetic mean, geometric mean. I could have also said 1 plus y is greater than or equal to 2 times the square root of y. And I could have said 1 plus z, and then I could have just multiplied the three of them together. And then I get 1 plus x, 1 plus y, 1 plus z. So 8, remember? 1 plus x, 1 plus y, 1 plus z is equal to 8.
Oh, that's a bit huge.
Yeah, where's the fun in that one, though?
It's so beautiful.
Yeah, I know it's a lot quicker and a lot easier and probably a much smarter way of doing it, but the other one's beautiful. Yeah, like the other one that just looked really... Oh, maybe it's just me, all right. Let's say, a lot of... Don't get fooled into thinking you're always going to use this arithmetic mean geometric. It does come up a lot, but it's not always the way of solving them. Oh, let's do this one, for instance. Oh, it's 2 ends. Okay, how are we going to manipulate this little one? A plus b, we know is greater than or equal to 2 times the square root of ab. But I'm also going to get 1 on a plus 1 on b. And that's greater than or equal to 2 times the square root of 1 on ab. Square root of ab cancels with the square root of 1 on ab. And I now have that this product is greater than or equal to 4. So I can rewrite that to be 1 on a plus 1 on b is greater than or equal to 4 on a plus b. Okay? So in case you haven't worked out, I'm trying to do the back end of the inequality. I could have said 1 on b plus 1 on c. I could have said 1 on a plus 1 on c and add them all together and divide by 2. Oh, look, we got it. Now the other end of the inequality. Well, you might be thinking, why on earth am I doing it this way?
You will.
No, I suppose I'm looking at the denominator. See how there was 2 terms in the denominator? So I used the arithmetic mean, geometric mean with 2 terms. I've now got this expression with 3 terms in the denominator. So I'm using it with 3 terms. Exact same idea, but I'm doing it with 3 terms. But of course it now turns out to be greater than or equal to 9. Okay. So what we now know is 1 on a plus 1 on b plus 1 on c is greater than or equal to 9 on a plus b plus c. Oh, excellent. But what about this bit in the middle? How about instead of a we'll put a plus b, instead of b we'll put b plus c, instead of c we'll put a plus c. And there's my equality. It becomes 1 on a plus b plus 1 on b plus c. 1 on a plus c is 9 on 2 lots of a plus b plus c. Oh, hang on. If I multiply both sides by 2, oh look, I've got the other end. Okay. How are you going to do this one? Arithmetic mean. 2 things added together will always be greater than or equal to 2 times the square root of them multiplied together. And when you multiply a with 1 on a, you get 1. And so there you go, it drops out straight away.
Yeah.
Of course, could have done it another way. We could have done it square root of a minus 1 on the square root of a squared, which gives me that, which gives me that. I mean, could have done it that way. Okay, we're now going to show that b plus c on a plus c plus a on b plus a plus b on c is greater than or equal to 6. But remember, this is what we know. A plus 1 on A is greater than or equal to 2. What would you like to replace? See, B plus A on B would be greater than or equal to 2. But hey, that also means C on A plus A on C is greater than or equal to 2. C on B plus B on C is greater than 2. Add them all together, and you've got B plus C on A plus C plus A on B plus A on B on C. We're now going to show that A on B plus C plus B on C plus A plus C on A plus B is greater than or equal to 3 on 2. So we just proved that. But hey, let's replace A with B plus C. Because now I want 2 terms in the denominator. Right. Down here,
How did I get from there to there?
well, the A was replaced with B plus C.
Yeah.
The B was replaced with A plus C. The C was replaced with A plus B. Voila. Alright, I'll put you out of misery. Okay, there's a nice sheet that I put in the handouts there. It's nice because it's got work solutions as well. So it's not a bad one to work through to try and get your head around this. Then there is the Cambridge, and Patel has some as well.